All right, so let's get started here. We're going to be doing our exam 4 review today. So just to be clear, exam 4 is going to be on chapter 10, our discussion where we initially introduced alkyl halides. Most of our reactions in this chapter focused on forming alkyl halides. And then we moved on to our substitution versus elimination. These are reactions of alkyl halides. Right? We have that competition between substitution and elimination. We said it depends on both what alkyl halide you're using, but also on what nucleophile or / base you're using as well. All right. So our goal is to just kind of practice as many of these as we can today, sort of focusing first on this alkyl halide chapter, since that was the one that we did, the longest ago. All right. And the first reaction that we had for our formation of our alkyl halides was taking an alkane and reacting it with one of these chlorine radicals, right? So if we take chlorine or bromine in the presence of light, we create these radicals, and they will react with those very boring alkane functional groups. All right, so step 1, we got to predict all possible products that we can get in these halogenation reactions. Remember, we can substitute any one of these hydrogens for a halogen, all right, but only some will produce distinct products, others might fall into the same category. So step 1 is to figure out how many distinct products we get from our radical halogenation reaction. Once we have those products, then we can actually calculate our percent composition using our reactivity factors here. And since we're talking about chlorine, we put chlorine. I give you those values for chlorine. These aren't anything you have to have memorized. They'll be given to you on your constants page. All right, so everybody take a second. Step 1, predict all of our possible products. Step 2, do the calculation to determine the percent composition of each one of those products. All right, how many possible products do we get? 3. Awesome. So we have, similar to how we did NMR, these are chemically indistinct carbons. So if I chlorinate either one of those, I would get the same product. These are chemically indistinct. If I chlorinate either of those, I would get the same product. And then this one sits all by itself. All right, so our 3 products would be if I put a chlorine on each one of those 3 sites. All right. And then how are we going to determine our percent composition? As we sort of noted, it's going to depend on our reactivity factors. All right, so just to go through, we need to figure out what carbon we have here, primary, secondary, or tertiary. Our green ones are what? These are primary carbons. Our red ones, secondary, and the orange one, also secondary. Now, these are both secondary carbons, but I'm going to treat them separately in my calculation because they would lead to different products, right? So I'm going to have to do 3 calculations here, one for each one of my distinct products. Regardless of the fact that these are both secondary, I don't lump them into the same group because they'd give me different products. All right, cool. So like we said, it depends on our reactivity factor. What's that other component, though, that it depends on? The number of hydrogens. Right? So it's going to be the number of hydrogens multiplied by that reactivity factor. All right? Divided by the sum of that same calculation for all of our possible products. All right, and by number of hydrogens, we mean the number of hydrogens that are sitting in these groups in my product or in my reactant here. So I could substitute any one of these 3 hydrogens to get that 1-chloropentane, or I could substitute any one of these 3 hydrogens to get that 1-chloropentane. So in this group here, my green group, there are 6 possible hydrogens times that reactivity factor of 1 divided by that sum total. I guess I should be good, times 100 because we're talking about a percent. All right, so I'm just going to start building my denominator here. 6 times 1. Okay, going on. My red group has how many hydrogens in it? 4 times that reactivity factor, which is greater for our secondary carbons. Get a reactivity factor of 3.9. All right, so I'm going to add that to my denominator here. 4 times 3.9. Then we got one more term here. I'm going to use that same reactivity factor of 3.9, but now there's only 2 hydrogens in that group. All right, and I'll use the same denominator for each one of these calculations here. Cool. So there's my setup. My number of hydrogens times that reactivity factor for each one. All right, so punching this into the calculator. All right, my first one here, I get a percent composition of 20.4% of that 1-chloropentane. My next one here turns out to be my major product, my 2-chloropentane. I'll get about 53.1% of my product as that 2-chloropentane. All right, and then lastly, the rest of it, the remaining 26.4% is my 3-chloropentane. Cool. So these radical halogenation reactions, first of all, we did have a mechanism. For the sake of time, I'm not going to go through our whole mechanism, but this is one that has the little star next to it, our radical mechanisms. We'll do a little bit of our fishhook arrow practice here in a second, but nonetheless, I can ask you both what all of the possible products are. Remember, we can substitute any one of these hydrogens for our halogen. That would give us our possible products, and then we can go a step further and actually calculate our percent composition using these reactivity factor values here. All right, so the next one is what's called an allylic bromination reaction. All right, so this is when we have an alkene and we use that NBS, N-bromosuccinimide. All right, this is another radical reaction. Importantly, what our NBS does is it produces bromine radicals. We talked about even how in radical halogenation reactions, bromine was a lot more selective of those more substituted carbons, right? Our values for bromine were like 1, 84, and 16 something off the top of my head. Some huge numbers, right? So very selectively reacts with our more substituted carbons. When we have an alkene, it's also very selective, but for the allylic position. Remember, those allylic hydrogen bonds are much weaker than all of our other carbon-hydrogen bonds. So this is specifically going to react at the allylic position, which is where? Carbons 1, 2, 3, 4, 5. Which one's allylic? This is our allylic position. These ones about the double bond we call vinylic positions. It's the one removed that we're talking about. That's our allylic position. All right? And so in this reaction, we're going to form this allylic radical. So I'm going to put my intermediate down here. That radical will react with our halogen, and we will brominate that allylic position. All right, now these ones were a deceptively big pain in the butt here, because not only do we get that original allylic position that gets brominated, we also have to worry about the resonance of this free radical with our carbon-carbon double bond. So there is an additional product that we get because of that resonance. I want everybody to take a second and do my resonance jump. Give me my other resonance contributor here for this allylic radical, and then our second product here that we get from our reaction with NBS. All right, so see if you can't finish this one off. All right, so I'm going to show my resonance jump here. Importantly, I'm going to get a new carbon-carbon double bond that's going to form one of those electrons being from my free radical, the other one being 1/2 of this carbon-carbon double bond here. So one of those electrons jumps over here to form my new double bond. The other one jumps over here, forming my free radical. All right, so if I'm going to draw my new positions here, let me get rid of these. My carbon-carbon bond is now over here, and my free radical is on the end here. All right, so what we see is our double bond and our free radical kind of changing positions here, swapping positions. All right, so that last product, just to keep these carbons color-coded so we can see, that last product here would have our bromine all the way at the end. Okay. Importantly, this new carbon-carbon double bond is formed between two electrons, one of them being what was my free radical, and the other one being 1/2 of this pi bond. The other half of that pi bond is now sitting just on that carbon atom. All right, so these were these allylic bromination reactions. where we have to brominate the allylic position and we have to do our resonance jump of that allylic radical in order to create our other product. And I could have made this even worse. For the sake of time, I just cut it down to this with only one original allylic position. But if we had two original allylic positions, you would have to brominate them both. All right, so again, ways that we learned how to create alkyl halides. There was another set of reactions that we learned, and that was turning alcohols into alkyl halides. And we had four different reagents that we would use to do it. Either what's called cyanochloride, phosphorus tribromide, hydrochloric acid, and hydrobromic acid. And depending on our alcohol, we would use a different choice for this reaction here. So everybody's going to take a second. Here I've converted alcohols into alkyl halides, and you're going to take a second and pull from that reagent bank. Tell me which four of these I should be using. All right, so let's look carefully here. We got four different reagents here. Importantly, we have two different halogens that we've been using. We can either chlorinate or brominate these alcohols, or rather substitute that hydroxyl group for a chlorine or a bromine. All right, so in terms of our reagents here, what does what? Let's use our context clues. Thionyl chloride is going to add what to our molecule? The chlorine. And which other one would add a chlorine? The HCl. And so our bromines would be our phosphorus tribromide or our hydrobromic acid. Okay, so then what's the difference here? Both thionyl and hydrochloric acid add chlorines to the ring. So which one would I use for each of these alcohols here? It depends on what? Substitution, exactly. All right, so this alcohol here is a primary alcohol, whereas this alcohol here is a tertiary alcohol, and that's going to make all the difference in the world in terms of which one of these reagents I pick. All right. The thionyl and the phosphorus tribromide, these are for primary or secondary alcohols, whereas our hydrochloric acid and our hydrobromic acid are for tertiary alcohols. And at the time, we didn't really know what this meant, so we didn't go too far into it, but that's because our thionyl and our phosphorus tribromide, they react with SN2 mechanisms, and we know that SN2 mechanisms are preferred by primary and secondary alcohols, or primary and secondary alkyl halides, same thing for alcohols. All right, and tertiary, it's because these react with SN1 mechanisms, forming those carbocation intermediates. All right, so at the time we didn't know what these were, so we didn't spend too much time on them, but now that we do, we can go back and tie it in. Because of our substitution mechanisms, we have a different preference depending on whether we're talking about primary or secondary versus tertiary alcohols. So in this case here, I'm going to want to use that thionyl and in this case here, I'm going to want to use that hydrochloric acid. All right. Our secondary alcohol here, we're going to have to use that phosphorus tribromide. All right. And then what about this last one here? All right. This is a secondary alcohol, right? But it's not just secondary. It's kind of special. It's also allylic. So you could use either phosphorus tribromide or you could use our hydrobromic acid. Either one would work. That carbon is accessible enough that you could react it in an SN2 reaction. However, it also forms nice stable carbocations, so you can use that hydrobromic acid instead. Okay? Now, one of these, though, from a practical from our pencil and paper standpoint, great. They both work perfect. If you're running a lab, one of these is definitely more preferable than the other. All right? And that is just when kind of practicality and cost come into play here. Per the same volume, you're probably spending $4,000 a liter for phosphorus tribromide compared to $50 for HBr, right? So from a practicality standpoint, there's a very big difference. We wouldn't want to use these fancy little reagents unless we absolutely had to. We always would rather go for the cheaper method if we could get away with it, right? So in this case here, we would want to use our hydrobromic acid, all right, because we can put up here, now we've talked about this, we know that our allylic and tertiary will happily go through those SN1 mechanisms. All right, and that's a little bit nitpicky in terms of what I would expect you to appreciate for an exam, but nonetheless, just to kind of throw it out there, it's always important to think practically speaking when we're talking about our pencil and paper chemistry. It's kind of easy to get lost on just turning stick figures into other stick figures, right? We want to think about actually doing this in the lab. Okay, there was another consideration that we had with these because these go through these SN2 type mechanisms. Doesn't matter for primary alcohols because they don't have any stereospecificity, but if we did use a stereospecific alcohol, we want to be able to predict our products here. All right, so everybody take a second. Give me my products of these reactions. All right, so again, my thionyl chloride is going to substitute that alcohol group for a chlorine, whereas my phosphorus tribromide is going to substitute that alcohol group for a bromine. But just like our other SN2 type mechanisms, we need that stereochemical inversion. All right, so when my alcohol group is on a wedge, I got to flip and put those new substitutions on a dashed bond. Cool. All right, and then there was one more reaction from this chapter that kind of sat a little bit different than the other ones because it actually used alkyl halides as reactants. And these are these Gilman reactions. All right, these Gilman reactions use these organometallic compounds here, where we have these metals in our ring. All right, not in our ring, I'm sorry. There's metals bonded to our carbon. All right, so everybody take a second. We'll copy down our chemical equation here, and then I want you to go through and label your nucleophile and your electrophile, specifically identifying your nucleophilic site and your electrophilic site. All right, what's our electrophile in this reaction? The alkyl halide or the Gilman? The alkyl halide. When you see an alkyl halide, the first thing you want to think are these things are good electrophiles. Specifically, where's my electrophilic site? The carbon bonded to the halogen, because the halogen itself plays the role of a leaving group. Cool, so if that's my electrophile, this one's my nucleophile. And what's my nucleophilic site? Yeah, the carbon that is bonded to our metal. Remember, carbon we don't really think of as being very electronegative, but that's because we're used to comparing it to all the other non-metals. Compared to copper, carbon is very electronegative and pulls all that electron density onto itself from that bond. All right, so what key thing we want to have in our mind for our Gilman reactions are that these create new carbon-carbon bonds. We do not have very many ways, in fact, only one other way of deprotonating a terminal alkyne and reacting it with an alkyl halide to create a new carbon-carbon bond. So this is one of these few ways that we have to create new carbon-carbon bonds between our electrophilic carbon and our nucleophilic carbon. All right, so since we're creating new carbon-carbon bonds, our product's going to be all big and ugly compared to our reactants. So counting our carbons, keeping track of our carbons is really important. All right, we're going to identify those 3 carbons from my electrophile. I'm going to start by redrawing that. And when I draw that new bond in there, what must live on the other side is that nucleophilic carbon. So then I need to make sure to include all of my carbons from my nucleophile. So that's 1, 2, 3, 4, 5 total with the little branch on the end. All right, so 1, 2, 3, 4. 5th one's got a little fork on the end. Go back and double check. 1, 2, 3. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Go back and count carbons. Really important. All right, and the other thing about the Gilman that we noted is that you can use alkyl halides or alkenyl halides where that bromine is attached to a vinylic carbon. All right, and importantly, these reactions preserve your alkene stereochemistry. All right, so everybody take a second and give me my product of this second Gilman reaction here. All right, so we're again going to create a new bond between our nucleophilic carbon and our electrophilic carbon. So I'm going to start by redrawing those 3 carbons from my electrophile. And importantly, when I draw that new bond in there, I want it pointed in the same direction as my carbon-halogen bond in my reactant. All right, so these are going to be on the same side here. Now I have to include those 1, 2, 3, 4, 5 carbons total. So there's 1, 2, 3, 4, 5 carbons total. All right. To be clear, you could have drawn your other carbons pointed in this direction. That'd be fine. The most important thing is this new carbon-carbon bond has to be pointed in the same direction as your carbon-halogen bond. All right. Now, somebody asked me a really good question now that we've talked about elimination reactions a bunch, which is why does this one form if it's the less stable alkene? Because it is indeed less stable than the E isomer, right? This big bulky group here would rather be on this side over here where it has more room. Importantly, these reactions, they always preserve stereochemistry. They don't give it the opportunity to form in the other direction, all right? Unlike our elimination reactions where it kind of samples all these different possibilities and then picks the most stable one as the major product, there is no sort of sampling of different stereoisomers here. We have to preserve our alkene stereochemistry. And honestly, the reason for that, when I've looked into it a little bit, it seems very complicated. It has to do with like some weird coupling between the copper and the carbon double bond, whatever. We don't know our mechanism for it. What we need to remember is that these reactions will preserve our alkene stereochemistry. Whatever stereochemistry we start out with, whatever direction our carbon-halogen bond is pointed, our new carbon-carbon bond is going to be pointed in that same direction. Okay. Let's jump to chapter 11 now. And the very first thing that I want everybody to do is to turn to a new page in your notebook, and you're going to fill out from memory one of these charts right here. All right. SN1, SN2, E1, or E2, or some combination of them for primary, secondary, and tertiary alcohols. What would we expect if we had a strong base, weak nucleophile? Strong base, strong nucleophile, weak base, strong nucleophile, or weak base, weak nucleophile. All right, take a second to fill out this chart here. All right, again, this is, I'm telling you straight up, going to be one of your questions on your exam is making sure that you know how to fill out this chart here, because this is our little cheat sheet that we use to go on and do all these problems. Oh no, so good question. Is it going to look just like this? It's going to be very similar, although you can guarantee that I'm going to mix up these columns here because I'm not trying to have you memorize putting one thing in a specific box. I need you to know that strong base, strong nucleophile, and primary leads to a certain combination of our reaction mechanisms. So exactly sort of the same here, but I'm going to swap all these columns around. All right, so if we're taking a look at this chart here, there's two columns that are kind of easier to fill in than the other two, and that is our when it's like bad at one but good at the other, right? So if it's a weak base but a strong nucleophile, that's going to prefer what? Substitution or elimination? Those are substitution. Nucleophiles like substitution, bases like elimination. Well, if it's a weak base but a strong nucleophile, it's going to prefer substitution. All right, and then we got to consider our primary, secondary versus tertiary here. Primary and secondary will undergo SN2 reactions, while our tertiary will undergo SN1 reactions. All right, similarly, the other easy category being our strong base, weak nucleophile. These are good at being a base, but bad at being nucleophiles, so they're going to prefer elimination reactions. All right, the first two are pretty obvious. Also, they're not going to form carbocations, so those are E2 reactions. Our tertiary alkyl halides can undergo E1, but they can also undergo E2 if they have a nice strong base. And the carbocation formation takes a really long time, so if you have something in there that's a really good base, it will deprotonate that neighboring carbon very easily, leading to an E2 type mechanism. So all undergo elimination, all undergo E2. All right, the next ones are a little bit harder because there's a kind of a push and pull here. These are categories where they're either both good at being both a nucleophile and a base, or bad at being either. All right. So for our weak ones, the important thing to remember here is that weak will only react with carbocations, because these are great electrophiles. All right. So if it's weak base, weak nucleophile, it's not going to be able to react with our primary and our secondary because they don't form carbocations. Alkyl halides are just not good enough electrophiles. We need one of those great electrophiles, our carbocations. So what we see here is no reaction with primary, no reaction with secondary. All right. When it comes to tertiary, since they're going to be able to form those carbocations, we're actually going to get a mix. We're going to get a mix of our E1 elimination mechanism with carbocation intermediates and our SN1. We sort of pretended like they were 50-50, and we kind of threw out that caveat that really devils in the details of exactly what nucleophile base you're using, right? Some of them will prefer elimination a little bit more. Others will prefer substitution a little bit more, just depending how weak of a base it is in comparison. But we can go ahead, we're going to simplify things and kind of throw it in as if it was 50-50. All right, and then our last category here, these are now going to be reagents that are good at doing both. They're good at being nucleophiles and they're good at being bases. And the key thing here is more accessible implies more substitution. All right, more accessible, I guess just to be clear, I'm talking about my more accessible electrophile. Electrophilic carbon would imply more substitution. So primary alkyl halides with their most accessible carbons, they are going to prefer substitution and will only get a little bit of that elimination product. When we add that extra carbon on the other side, making a secondary alkyl halide, all right, these are going to flip. Now we're going to get a majority of our elimination product and just a little bit of that substitution product. All right, our tertiary alkyl halides, those electrophilic carbons are pretty much inaccessible. A nucleophile can't really get to them unless we give it enough time to form one of these carbocations here. But since we have that strong base present, we'll get an elimination reaction before our carbocations even get a chance to form. All right, so now let's use our cheat sheet chart here to do the rest of these here. So now we can do our, given an alkyl halide and a reagent, we can figure out what our product will be. All right, I'm going to change this here to that other one that we said. That tosyl group. All right, so we got to go through here and classify our alkyl halides as being either primary, secondary, or tertiary. In this case here, we have a primary alkyl halide. All right, maybe a little bit trickier is we have to classify our reagent here as being either a strong or weak base and a strong or weak nucleophile. So this hydrogen sulfide ion here is which category? So yeah, so it's a weak base, but a strong nucleophile. So first of all, how can I spy that it's a strong nucleophile? It's got that negative charge. All right. What makes it a weak base, though? It's a large atom. Yep, so this is our large atom. All right. Different from these other ones here. These were also weak base, strong nucleophiles. But how could I spy that these strong nucleophiles, because we have that net negative charge, how could I spy that these ones were weak bases? Resonance stabilized. All right, so these are these two things that we got to look out for that would have it fall in this particular category. We're looking for something negatively charged that's either attached to a large atom or is resonance stabilized. Both of those make them weak bases. All right, large atom, both of which go back to our Fario rules. All right. So here I guess now let's look at our cheat sheet. We got a primary, that's a weak base, strong nucleophile, so that's an SN2. All right, so now we need to substitute out that halogen for our SH. Creating what functional groups? Does anybody remember what we call these? Thiols. Awesome. All right. Here we have a secondary, not quite alkyl halide, but remember these tosyl groups here, you just want to think of these as being just incredibly good leaving groups. All right, just to sort of draw it out so we remember here, they're kind of these sulfate-ish looking groups. There's a bunch going on the back end here. All right, but super duper resonance stabilized leaving group here. So again, we have our weak base strong nucleophile. So again, we're going to expect to see an SN2 reaction. But now I'm starting out with a stereospecific reactant here. So when I draw my product, I'm going to have to remember to do my stereochemical inversion and flip that dash to a wedge. All right, I'm going to be good and draw my nitrile group here linear, since it's got that carbon-nitrogen triple bond. All right, and then lastly, now we have a tertiary alkyl halide. Since it's a tertiary alkyl halide, we have an SN1 elimination reaction here, which means what are we going to do? When we had SN2, we inverted our stereochemistry. What about SN1? We're going to lose it. All right, so we're going to form that carbocation intermediate and lose our stereochemistry. So let me just show one big mistake that I saw people doing was they were like, all right, great. I lose my stereochemistry. So here's my product. All right. So first of all, what's wrong with it? Where am I supposed to have a wedge, though? I thought I lost my stereochemistry. Yeah, only about my carbon that was actually involved in the reaction. Only about that carbon that actually formed a carbocation. This carbon over here wasn't involved in the reaction at all. It doesn't get touched in this reaction. So that's going to stay on that wedge. Whatever my stereochemistry is, away from my reactive site, I'm going to keep. All right, and then importantly, the other kind of tricky thing here, because this is a big, ugly nucleophile, I'm making sure to attach that electrophilic carbon to my nucleophilic site, which in this case is that negatively charged oxygen. Cool. All right, so let's do 2 more here. All right, so importantly, these are now strong bases, but weak nucleophiles. So these are going to prefer our elimination reactions. All right, when we do our elimination reaction, so I want to do this example in particular so we can, figure out a bunch of our different elimination products and then classify them as being major or minor products. All right, remember, in order to undergo an elimination reaction, you're going to lose your halogen, your leaving group, of course, but you also have to remove a hydrogen from a neighboring carbon. And we got 2 neighboring carbons here. So I'm going to have one elimination product where I eliminate to the left, and another elimination product where I eliminate to the right. All right, but we're not quite done there. We also need to make sure that all of our stereoisomers are represented as well. So I'm going to go through and figure out whether I'm looking at the E or the Z stereoisomer here. So which one is this one? E, Z, or trick question? Trick question. How do I know it's a trick question? the two hydrogens, right? Anytime you got two identical groups on the same carbon, we could swap them and we'd have the same thing. So this one has no stereochem, which means there's going to be no additional product. All right, but this one here is which one, E or Z? This one is the E stereochemistry. So I'm also going to have to include our Z stereoisomer. All right, so then how do I draw my other stereoisomer? You're going to pick either side of that double bond and swap those two groups. So I could either swap this methyl group and this hydrogen, or I could swap this methyl group and this ethyl group, whichever one I wanted to pick. All right, in this case here, I'm going to go ahead and swap the ethyl and the methyl so it's a little bit more obvious. Okay, now I'm going to have my methyl group pointed up and my ethyl group pointed down. This is my Z stereoisomer here. And then if we wanted to note major or minor products, we want to first look at our substitution of our double bonds. This one's mono-substituted, whereas both of these are di-substituted. So what's better, mono or di? Di. So this one's going to be a minor product here. All right, and then between my E or my Z, which one's more stable? E, I got that big ethyl group on the opposite side of that methyl group. So this is my major product, and this is my minor product. Okay. On this next one, this one might be a little bit tricky here. Let's say that I'm going to play the same game. I'm going to say, all right, I got this carbon over here and this carbon over here. So let's play that same game where we form our double bond on the left. And we form our double bond on the right. All right. However, only one of these are actually going to be the product that we get here. All right. Why? What's wrong with one of them? We got a broken octet. So everybody's organic chemistry brain needs to explode looking at a structure like this, right? This carbon has too many bonds. 1, 2, 3, 4, 5. Yeah, right. That's not going to happen, right? The problem is there's no hydrogen over here on the left that I can remove in order for this elimination reaction to occur. So we can't just kind of blindly be dehydrating in both directions. We have to remember here that we're removing a hydrogen, so only this product would form as my elimination here. All right. For the sake of time, I'm just going to kind of quickly... Another thing that I could ask you is the stereochemistry of an E2 reaction. Let's say that instead of giving you this, which would represent a racemic mixture, I instead gave you a stereospecific one. So my bromines got a specific stereocenter, and my methyl groups here got a specific stereocenter. All right, well, in order to figure out, and we're just going to do our major elimination product. All right, that's going to be the more substituted one. So I want to look down this carbon-carbon bond here. Okay, and create a Newman projection. Okay, this is my front carbon. This is my back carbon. Front carbon, back carbon. On my front carbon, that methyl group is pointed down. On my back carbon, that ethyl group is pointed up. All right, so then fill in these spots here and tell me if we're going to get our elimination product. right, so my leaving group is pointed out of the page, so it's over here on the right. My methyl group is pointed into the page, so it's on that back carbon on the left. And am I going to be able to get a dehydration in this rotational conformation here? No, because what's the rule? Our leaving group and our hydrogen on the opposite carbon have to be anti to one another. So in order to get my dehydration reaction, my elimination reaction, I'm going to have to rotate. And you can either rotate the back or the front carbon. It doesn't really matter. On your homework, I was specifying which one to do. We're going to do the back one. All right, so that means my hydrogen's going to need to be rotated in position. My methyl group's now going to be on top, and my ethyl group down there. All right, so I'm going to keep everything on that front carbon the same, but now I'm going to rotate so my hydrogen's over here, my methyl group up here, and my ethyl group down here. All right, so just keeping track of those high priority groups on either one of my carbons here. My front carbon's high priority group was that methyl group. My back carbon's high priority group was that ethyl group. All right, and we can see that we're going to have to draw them on the same side of my new double bond that forms. All right, so I'm specifically going to form the Z stereoisomer here as my major elimination product. All right, red and orange have to be next to each other. Cool. All right, so two quick things that I'm going to tack on to the end here. We've been talking a lot about our alkyl halides, and I just kind of never explicitly brought it up here. We had primary, secondary, tertiary, or these allylic alkyl halides here. But these were all bonded to what type of carbons? Like, what's my hybridization on these carbons here? sp3. And sp3 are the only ones that are going to undergo elimination or substitution reactions. So these are great examples here of molecules that have these sp2 hybridized carbons. All right, my leaving group is on an sp2. And these you would see no substitution or elimination reactions. All right, if it's an sp2 hybridized carbon, all right, your leaving group will not leave. These cannot be backside attacked in the same way that our sp3 hybridized carbons can. They also do not form stable carbocations like our sp3 hybridized carbons can. So these are not going to have any substitution or elimination reactions. You're not going to be able to remove this leaving group here from an sp2 hybridized carbon. Okay, and then the last thing that we didn't talk about is our solvent choice. For substitution and elimination reactions. All right, it turns out that you can increase your efficiency of these reactions by being really clever with your solvent choice. All right, these reactions, they work best with polar aprotic solvents. All right, so polar we've talked a bunch about, right? We've learned how to spy polar versus non-polar molecules. We even went so far as to kind of put them on a sliding scale here to talk about things that are, yeah, they're technically polar, but they're only weakly polar, et cetera, all right? So first of all, why do I need a polar solvent? Well, because of my nucleophile. Because all of these reactions involve some nucleophile, some base, which either have a charge, so they're definitely polar, or they at least have a lone pair in an asymmetric geometry, so they're polar. All right, so our solvent has to be polar so that it's compatible with our nucleophile. All right, so nothing too crazy there. But what about this second keyword here, aprotic? What does that mean? So yeah, so the A means not proton, but really it specifically means, it doesn't mean that there's no hydrogens at all. It specifically means that this solvent cannot hydrogen bond. Deuterium actually can still hydrogen bond because the D is still a hydrogen atom. Holy cow, sorry. I zoomed way too much out. Okay. We'll see some examples of some aprotic solvents, things that can't hydrogen bond here in a second. But why is it important to be aprotic? All right. So again, aprotic meaning it cannot hydrogen bond. All right, so why don't we want it to be able to hydrogen bond? Well, because hydrogen bonds are these very strong interactions, and they will help stabilize that nucleophile, stabilizing it so much that it won't want to react with our electrophile anymore. All right, so we don't want it to hydrogen bond and stabilize our nucleophile. All right, so let's use a free energy diagram to illustrate the difference here. All right, so first we're going to compare a polar protic solvent, right? One that can hydrogen bond. And we get a pretty normal looking free energy diagram. Our reactants a little bit lower energy than our products. I'm sorry, our products a little bit lower energy than our reactants. All right, but now we're going to use a polar aprotic solvent, which again is going to destabilize that nucleophile, which remember is one of our reactants. So when I draw my energy level for where I'm going to start out here, if my reactant is destabilized, does that lead to an increase in energy or a decrease in energy? What does it mean to be destabilized? What's good, low energy or high energy? Holy hell, okay. When we say low energy in chemistry, that means good and nice and stable. High energy is bad, low energy is good. All right, so if we say something destabilizes, that means it raises the energy of that reactant. All right, but it doesn't really change our product energy. So instead, we have a smaller activation energy barrier, and we have a more favorable, from a thermodynamic standpoint, reaction. This has a smaller activation energy, and it has a larger negative delta G because of that solvent choice, because we've destabilized that nucleophile with that aprotic solvent. All right, so then given a list of solvents here, I want you to classify these as being polar or nonpolar and being protic or aprotic. All right, water is what? Polar or nonpolar? Polar. And can it hydrogen bond? Yes, so this is a polar protic solvent. What about this thing here? What is this molecule? What is it? Methanol. You also see this written MEOH, right? A methyl group and an alcohol. Can alcohols, so first of all, they're polar. Can they hydrogen bond? Yes, so this is also a polar protic solvent. All right, this thing here, for $1 million, what functional group? Ester, nice. Yeah, all right, very similar to an ether. If we got rid of this, it would be an ether. With that carbonyl group on there, it's an ester. And this is what's called ethyl acetate. This is a really popular kind of up-and-coming organic solvent. We'll talk about why that is here in a second. Is it polar or nonpolar? Polar. What gives it away? That carbonyl group. All right. This thing right here is kind of weakly polar in and of itself, but yes, a carbon-oxygen double bond acetone, right? A good polar solvent. This is a good example of a polar aprotic solvent. This cannot hydrogen bond. It doesn't have one of those oxygen, hydrogen, nitrogen, hydrogen, or fluorine hydrogen bonds. Dichloromethane. Polar or nonpolar? Technically it's polar, but we know from the lab that it is like just barely polar, right? I mean, it does have a tiny little dipole moment, but yes, we would call this weakly polar at best. But it is indeed aprotic. It cannot hydrogen bond. All right, what about benzene here? Yeah, this is just straight up nonpolar. All right, technically aprotic, but it's nonpolar, so definitely can't hydrogen bond. Okay. And then what about this thing here? Another kind of up and coming, what's called DMF, or dimethyl formamide is what? Polar or nonpolar? Polar, we again got that carbonyl group. And then can it hydrogen bond? So remember, in order to H bond, you must have either a fluorine hydrogen bond, an oxygen hydrogen bond, or a nitrogen hydrogen bond. Does this have any of those? No. So this is another great polar aprotic solvent. Okay? So these would be great to use for these substitution and elimination reactions. They're still polar, but they are not protic. They can't hydrogen bond. They are aprotic. These two are really popular, kind of like up-and-coming sort of things. Dichloromethane, which we use a lot, but it's kind of getting phased out here. These are what are considered, actually all of these here, are what are considered green solvents. What do we think we mean by green? Well, they're all organic, right? Good for the environment, right? Or I guess strictly speaking, not terrible for the environment. Dichloromethane, remember how we have to segregate our halogenated waste and pay more to get rid of it? That's because that's much more detrimental to the environment. Benzene is also one that was really popular to use back in the day until they realized that it is just crazy carcinogenic. All right, so these are these new green solvents, meaning there's no halogens and no benzene rings, both of which just turn out to be terrible for the environment. All right, so you'll hear this term green solvent thrown around a lot. Ethyl acetate kind of being used to phase out dichloromethane. Our DMF, same sort of idea. These are both these polar aprotic solvents that are also considered to be green solvents. There are no halogens and no benzene rings. Cool. All right. I know it's very sad.